Hi. The problem for for this mini lecture is how to detect the hazardous behavior, hazards in a system before you build it, before you implement it in hardware. Good news is that the dynamic hazard can be eliminated or is eliminated if you use only sum of product of sums and their not only nor only transformations, but the transformations must be performed in the way I've presented in one of the mini lectures. Okay, only these transformations don't introduce any hazard into the target device. Okay, so as you can see, we've got a sum of products, and the output gate is a sum. And when the hazard occurs when you've got one of the input A and on the another not A, or B and on another not B, and so on. So you sum the signal and its inversion. And you must detect all these situations. And the analytical method allows you to do it. Analytical method is the following. You must verify if there is a hazard for each variable, for each input separately. So let's start with A, then to B, C, and D. So A, with respect to A. And then you must redraw Y to have it in the form, let's say, X times A plus Y times not A plus Z. And the bigger upper X, Y, Z contain all the remaining variables, inputs, but not A. Okay, so returning to our example, you've got a single A here, so your X is not B, not C, plus your Y is not BD, and Z, upper Z is BC. It is upper Z. So let's denote it X, Y, Z. And the condition is that you add at the output A plus not A only. Okay, that's the condition for hazard. So hazard would occur when you've got X, upper X equal to 1, upper Y equal to 1, and Z equal to 0. In this case, you would have A plus A on the output gate. So, and as you remember, A is delayed with respect to A, so the hazard will occur. So let's express these conditions using variable names, the other variables. So when X is equal to 1, when there is B equal to 0 and C equals 0. Okay, that's not C is 1, not B is 1, multiplied together with each other is 1. So 1 times A gives you A. Alright, so it is a first condition, and the 3 must be satisfied at the same time. When Y is equal to 1, when the B equals 0 and D equals 1, and the third condition, when Z equals 0, when B equals 0, or not and, but or C equals 0. Okay, this is very important. And analyze it. They are satisfied or they are not compatible, not consistent conditions. From the first, B must be 0, B 0, and this is here the same. This is satisfied because it is ORed. So the first is B0. The second C0 and D1. Okay, can be satisfied at the same time. So if you have B0, 0 on input B, 0 on input C, and 1 on input D, and if you change A, you will observe hazard, static hazard. So glitches will be present on the output. So there is a hazard when you put this value on input and you will change A. You will observe static hazard. Okay. How to eliminate this hazard? You must, of course, change and expand this equation, add some logic. You must pay for it. And how to do it? You simply must add this product, upper X times upper Y, coming from these two. And you can use simplification methods from Boolean algebra, because you've got B inverted twice. You can replace it by a single B inverted. Then you've got a C naught and D. So to eliminate this hazard, the rule is you must add the product of upper X times upper Y and do some simplifications. Alright, so there was hazard with respect to A, but if you add some logic, okay, additional product, this sum, you will eliminate it. Okay, let's go to another one. B. And B, as you can see, is the following, and Y is equal to C times B. Let's return to this. And you must factor out not B. And in the parentheses you will have not AD plus A not C. Not AD, not AD plus A not C plus A not C. That's and times not B with respect to B. Now we are dealing also with B. Okay, this is our X, this is our Y, and Z, because it's not here, nothing here, as Z equals 0 by default, so it is a condition satisfied for hazard. And let's expand it, and the condition is that C is equal to 1 and this, how to A not D equals 1 or A not C equals 1. Doesn't matter which one is satisfied. From this you've got A equal to 0 and D equals 1. From this you've got A equals 1 and C equals 0. You can take this or this because they are connected with OR. Okay, or quantificate. So if you look at C equal to 1, okay, A equal to 1 and D equal to 1, this is not important. It is even not compatible with this condition, but this one is compatible. So we can take this condition and this one. So from these two conditions, you've got the values for A, B, D, C, and D, for which the hazard occurs with respect to B. So, and then the condition is the same: multiply X times Z, X times Y to eliminate hazard. So let's do it. X times Y equals C times not AD plus A not C. You can multiply, use distributivity axiom, not ACD plus A not C. C, you can also use this axiom 3, axiom 4, and you know that C times not C is equal to 0. 0 times A gives you 0, so it is equal to not A, C, D. To be added to the first, you must add as well this one, not A, C, D, plus not A, C, D, to eliminate hazard with respect to B. What about C and D? I will wipe it out. And as the condition was expressed. Okay. Now with respect to C, and you've got B, Y is equal to B times C plus not A, not B, times not C plus not A, not B, D. And the conditions are B equals, let's take another color, the red one, B1. From this, A1 and B0. From this, A equal, this should be 0, so A should be 1, or B should be 1, or D should be 0. To have a Z, it is a upper Z here, this element. So let's have a look. These should be satisfied at the same time. And looking at these two conditions, they are not consistent. So cannot be satisfied at the same time. Not consistent. No hazard. Yes, you don't need to add anything. No hazard with respect to C. By changing C, you cannot observe glitches at the output, okay? Because the conditions for hazard are not consistent with each other. Okay. All right. So the last variable, the last input is input D. And by observing that you don't have not D, yes, there is also only D here. You don't have inverted D. That's why you can, yes, that the conclusion is no hazard. Because not D is not represented in the formula for Y. Okay, that's enough. That's enough to not have any hazard. So the conclusion is that without addition these two products, the function would have a static hazard behavior for A and D and B, and for the given values of the remaining of the remaining inputs, as I shown. And to eliminate static hazard, you must add addition to AND gate to produce this product, and all these products must be added at the output gate, which in this case must have two additional inputs for this element and for the red one. Okay, and Y is the same function but free of hazard. Thank you.